Alright, so let's get started. Hello everyone, I'm Shishidhar. No, I'm a PhD student associated with the Systems and Control Group at IIT Bombay. And I'm also the TA of course, EE90. So let's begin with the fourth review session of this course. Okay, so just before we start, let's recall the concepts that were taught in the week 4. So there were mainly 3 topics that were covered. One of them was determining the eigenvalues and eigenvectors. This one was determining positive definiteness. Yes, ideas and vice versa. Next one was stability of LTI systems. So in this we had input stability, asymptotic stability, and of course stability in the sense of reliability. So the first part is eigenvalues and eigenvectors of a matrix. Alright, so we already know that to calculate eigenvalues and eigenvectors, we first need to determine the characteristic equation, which is Si minus A, determinant of it equated to 0, or if you want to write it in terms of lambda, then lambda I minus A equals 0. Okay, so let's start with an example. So the matrix is a 3 by 3 matrix. It's minus 4, 1, 0, 0 minus 3, 1, 0, 0, 1, minus 2. Okay. Eigenvalues. Let's just form this matrix first. So it's going to be lambda plus 4, lambda plus 3, and lambda plus 2. And other value will be minus 1, 0, 0 minus 1, 0, 0. So the determinant of lambda analysis is given by lambda plus 4, lambda plus 3, lambda plus 2 equal to 0. AR. So this is already in factored form. It's minus 4, minus 3, and minus 2. So now these are distinct eigenvalues. Let's write that down. Okay, unique eigenvectors to each of these eigenvalues. Find those. So we have for lambda equals minus 2. We need to find the vector v1. So we need to v3, which is 0. Or it's going to be a 3 by n vector, so 0, 0, and 0. Minus lambda I minus 4 minus lambda minus 3 minus lambda minus 2 minus lambda. Zero vector then R3. The first equation of so for lambda equals minus 2, this becomes minus 4 plus 2 becomes minus 3 plus 2. Alright, so let's now see what v1, v2, v3 should be. So minus 3 v1 plus v2 equals 0. Then we have, okay, so this implies that v1 equals v2. Minus v1 plus minus v2 plus v3 equals 0, which implies that v2 equals v3. And then we don't have a third equation because this is a row of zeros. Okay, so we have two conditions and we need values of three variables v1, v2, and v3. So let's assume something. So t equals 1. This implies that v2 is also 1. This implies that v1 is going to be half. So this satisfies the eigenvalue equation. So for lambda equals minus 2, the vector v is half 1 and transpose. There are of course other choices for v1, v2, and v3, and this is just one of them. So if you want to write this down generally, we could have some constant c by 2, c and c. Where c is some v1. Okay, so similarly, there are two more eigenvalues, so let's complete those associated eigenvectors quickly. We have for lambda equals minus 3. 1 or plus 1. The equation is minus v1 plus v2 equals 0. Or simple as that, v1 and v2 are equal. And then the equation from these two rows is just that v3 equals 0. So the vector, eigenvector v is 1, 1, 0. Or some constant, for example, c prime, c prime, c prime. For the last eigenvalue, so this one and let's go 1, 0. First equation is simply v2 equals 0. And this is v2 plus v3 equals 0, which implies that it's v3 equals 0. And the last row implies that v3 equals 0, which I already said. So v1, there is no restriction on v1, so v1 can be any real value. So the eigenvector associated with lambda equals minus 4 is, for example, 1, 0, 0. Or some constant c double prime 0, 0. Just here. Questions involving the computation of eigenvalues and eigenvectors. And the rest of the elements of A matrix will remain as they are. So this is 1 and 0. So the determinant is simply 1 minus lambda, 2 minus lambda equals 0. So the eigenvalues are 1 and 2. Again, these are distinct eigenvalues. Eigenvectors easily, as we just seen in the previous example. So let's start with them. This is it. That both of these equations just gives this single condition, that is V2 equals 0. So V1 could be anything. So for example, it's 1, 0, 2, 0, or any, for example, in general, some constant c down 0. for lambda equals to less than 0, 1 and 0. This just gives a single condition that minus V1 plus V2 should be 0 or V1 should be equal to V2. So the eigenvector, the most simplest case would be 1, 1. Or some constant CC. Again, let's check the eigenvalue for a square matrix of space 3. So this is the A matrix 0, 1, 0. And 6. Characteristic equation is going to be minus lambda equals 0. So this becomes minus lambda, minus 6 minus lambda. And minus 7. Okay. So now we need to find the determinant. Minus 6 minus lambda. Right? That's 24. Let's check this again. X lambda plus lambda square is 4. Yeah. Minus 18 minus 3 lambda plus 24. Okay. This is minus 3 lambda plus 6. This is 0. Will be plus 3 lambda minus 6. So now we have a quadratic equation. 7 lambda minus 2. Three distinct roots or eigenvalues. Here have distinct eigenvalues. corresponding eigenvectors by the method that was just discussed in this example. So we have already seen an example of a 3 by 3 matrix and looked at how to find the vector v1, v2, v3. Okay. Start. You had some doubts, right? We determine the stability of the state space model by looking at the eigenvalues of the A matrix. So let's see. Our system have a state space model. I'm going to write down the matrices for it. So the A matrix is 0, 3, 1, 2, 8, 1, minus 10, minus 5, and minus 2. Similarly, we have B. Is 1, 0, 1. So the question is to find out or LHS that have S plane. Similarly, on the right half plane, okay, so since we are talking about poles, so what we are actually talking about is the denominator of the transfer function, and that is nothing but the characteristic equation. So we need to find out how many roots of the characteristic equation are in the left half plane, right half plane, and on the geometry axis. So let's see. First from this matrix, let's write down the non-linear elements first. So I'm going to be minus lambda. The determinant. Minus 3 times. And finally, the last method. So it's from the characteristic equation minus lambda. 2 lambda plus 10 here minus 10 plus 80 minus 10 lambda. This is 0, this is 0. It's 5 over. This is 5 distance. Now select it. And have the square minus 6 lambda minus 30. Minus. Okay. So it's simplified this. This 70 minus 10 lambda. So minus lambda. Then we have lambda square. Then we have 12 minus 11 pi. Next, this is color. Sorry. Let's calculate the characteristic polynomial. So this is going to be x5. Then we have minus 3. Right? And this is straightforward, so let's simplify this there. Minus this lambda minus square. Minus 6 lambda. Minus 7. Minus 2 lambda. And then plus 6. Minus lambda. Yeah. Hmm. Okay. Yes. All right. You have minus under cube. Minus 18. That's again minus 1. Okay. So this is 6. Okay. And you have plus 7 lambda plus 22. Okay. So there can be two ways to find out the location of the poles. Okay, so one of them is that which we have just done to determine the eigenvalues of this characteristic equation and then comment on how many poles are on the left half plane, right half plane, or on the imaginary axis. The other one is that you already have studied before in one course. So that is the Raoult criteria. So because we have to find out the poles of the transfer function, so we have this characteristic polynomial. By this I mean by creating the table of zero and directly determining the sign changes. So if I am and there are going to be some there's an easy method to determine the roots of the equation. Let's see. Minus 1 is there. Okay. So instead just let's just create a table. So this is a third order polynomial. So lambda cube, lambda square, lambda to the power n and lambda 0. Then we have minus 1 and plus 7. Roots and equity. So this entry is going to be and then we will just simplify this to the first PM 26. Okay. Then we have lambda 1, which is going to be 1 plus 26.3. So it's minus 17 minus 47 by 3 minus 0 of course. And then we have plus, this is just 26. Okay, so now let's see the sign changes. There is one sign change. Second one, okay, right. So it's a third order polynomial and we have three sign changes. So all of them are, I think, this is the basis of the sign change. What is the yeah. Just one sign change. So there are three eigenvalues or three poles, out of which uh, there are only two stable poles. And so this is on the left hand side, right hand side, and on the geometry axis. So there are no poles in them. You can also find out the roots of this equation and then determine the poles. Okay. So there are just some definitions that I want to clear first, and then we'll look at some examples. So the first question is, why do we need positive definite matrices? So just recall. Right? So recall from the lectures that we were talking about something called the Latimer function, and we were describing this as x transpose px. So x can be, so x are the states, so it can be a 3x1 vector, or for an n-dimensional system it could be an n-by-1 vector square matrix of size n. In addition to being a square matrix, we also take it to be symmetric, and we say that P equals P transpose. A symmetric matrix is positive definite. This is the symbol for it, showing that P is positive definite when there are certain conditions on the P matrix. Alright. So one of them is that if it is symmetric, then the determinant of P is greater than 0. Other one is that the eigenvalues of P are real because it's symmetric, positive because of positive definiteness of the matrix. And then the last one is that this form is always positive, and x transpose px is 0 if and only if x is identically 0. So observe that we are using this form, and this is also the form which we are using in the Lagrange function. So there are some features to check if this is positive definite. Of course, there are more as we have seen in the lecture. Okay. So we have this scalar function. So Vx is a function from Rn that is states from n by 1 vector space, and it gives you scale. So when is this function Vx positive definite? So Vx can be first. Of course, from here, this is greater than 0, or it's not 0, and x transpose Q is equals to 0. So from there, x is 0. Have negative definiteness. So when is this scalar function negative definite? When x transpose Q is strictly negative, and it is equal to 0, x is equal to 0. Then we have something called semi-definiteness. So let me just show you positive semi-definite. X transpose Px can be greater than equal to 0 even when x is not 0, and positive 0 when x is 0. This is an infinite condition. And similarly here, negative semi-definiteness. X transpose Px will be less than equal to 0 even when x is non-zero, and in the same condition. Alright. Now let's see some examples. First, give a function u of x, which is x1 squared plus x2 squared. So this is positive definite, right? So this is going to be always greater than 0 for x non-zero, and this is equal to 0 when this vector is exactly 0. And what is the P matrix here? So let's just write this down. This is actually x1, x2, okay, x transpose, and let's see, and this is going to be x1, x2. So the first criteria is going to be that this is symmetric. Let's see, P11, and then this x1 squared P11, x2 P12, x1, x2 plus identity difference from 0 to 1. So this is the simplest example of a random function. So given for example some nonlinear function. So this function f is nonlinear. We want to determine its stability. So we will do it via the Lyapunov function approach, and one of the easiest Lyapunov functions to consider is norm x squared. For example, we are in R2 here. So this is simply x1 squared plus x2 squared. If we were talking about the three-dimensional case, first check the stability by using this simple Lyapunov function. It may not always work, but this is the simplest one. This is going to be x1 squared plus x2 squared plus x3 squared. Okay. This was first. This function is a positive definite, semi-definite, or any of those other two options. So let's check. So this is going to be x1 squared plus x2 squared plus towards semester. The system, we already have this expansion. So we have this matrix, which is are going to be here and 2. Alright, so is this positive definite or semi-definite? Maybe negative. Sorry, 1. Always going to be greater than 0 because this is a square, so it can never be negative definiteness or negative semi-definiteness in this question. The question is it positive definite or positive semi-definite? Okay, let's see. There was a condition that x transpose px can be 0 for a non-zero x. So let's see. So it's a 0. That's a Sylvester criteria, so then that was next. But yeah, so it's a simple 2 by 2 matrix, so this is 1, and then this minus 0. Okay. So this can never happen. So it's positive semi-definite. Yes. Or if this is symmetric already, and then this is going into 0. Eigenvalue is positive and the second is exactly 0. Alright. This is positive semi-definite. Now there is this. So the ordinary function v of x is minus x squared, x1 plus x2 whole square. Okay, so this can never be positive. So what we're talking about is negative definite or negative semi-definite. That's nice. Okay. So the matrix is minus 1. So this is 0. Okay. Then plus this becomes minus 2. And this was this p times p1 towards ns2. So p1 towards minus 1. This is the first one, minus 2. And then the determinants is going to be minus minus one. And then we have minus 100. Sorry. Hmm. Determinant is 3. Hmm. And it's the diagonal value is first. And plus 2 and then this is an optional and this cannot be because the principal problem. So when once question yeah, so it's on the then we have the last example. And it's to yes, let's just go. Okay. So let's see. So we have to set the x to and the is positive definite. And we have it done like this. It has to be greater than 0 for x, non-zero. So let's see if there is any vector which is greater than 0. Oh, sorry. There is material. And x transpose to x is exactly 0. Only for a non-zero. Yeah, I think we can see from here that this is 0. Even for a vector line and 1 0, right? Yeah, this means opposite. Of course, not positive definite, not positive semi-definite. You can also come to P matrix and so x2 squared is no component for x1 squared, and this is going to be half. So you can just observe that the first number is 0. Right, so if this is clear, now we have some matrix, a 3 by 3 matrix. So let me just write this down. Then 1, yeah, minus, yeah. Okay, one of them is 0. Those should be strictly negative, like which is now about semi-definiteness. Of minus of Vx, minus x1 x2, then minus x2 squared. If this is negative semi-definite as we're claiming, then this should be positive semi-definite, right? In this case, V matrices, V matrix. Next one is and what's the determinant? Element is minus under 4. It's semi-definite number. Function V of x, that scalar function, is negative semi-definite. Yes, minus V of x is positive semi-definite. Should maybe describe some region in which we are operating. So, for example, if we want this to be strictly positive or greater than 0, then we are talking about a region where first quadrant. In that case, V of x is always greater than or equal to 0. So at x, 1, 0. Good. Let's start looking after this class. So your claim is that it is not a semi-definite. So here, so next to minus 1. And now we use the silver stress. Add the minus. So we have this and then this and the whole method. So then we have so it's going to be yeah. Okay, so all of the minus are possible. You have a positive definite. Okay, so I name a scalar function from the discrete matrix is a positive definite function. And with positive definiteness and eigenvalues, eigenvectors, and stability is a location of eigenvalues. Now we have another topic. So I'm going to write down a general form of an ordinary system. So let's say a differential equation is given by x dot equals to some non-linear function of the states and the input. And since this is a differential equation, we also need some initial condition. So I'm defining this to be x naught. Okay. Definition, which is an autonomous nonlinear system. So that is when we're considering system without any input. And again, it's some initial condition defined as x naught. For this function, so this differential equation. So for one, I think this video is getting paused. So let's go ahead. So for one, we have all the sufficient conditions for stability. Notice if these are met, these conditions are satisfied. So what is a stable system? Oh, sorry, stable equilibrium. So for this, we need a scalar function v of x, again going from some space Rn to the scalars R. First condition is that wave should be greater than 0 for x non-zero. And then wave should be equal to 0 exactly for x equals to 0. This implies that we're talking about positive definite degree. Okay. And the third one is that we can take derivatives of a v. So the function v is, or v has partial derivatives. So this is because when we talk about v dot, so it would be del v by del x times del x by del t. So we need these partial derivatives. And then the last condition is that when you compute v dot x, it should be negative definite. This implies that the equilibrium is asymptotically stable. So this means that v dot is negative definite. Or if you just want to talk about it is asymptotic stability or dash, but it's non-zero. And also in addition that the state x goes to the equilibrium. So what's the equilibrium of that nonlinear differential equation? When x dot equals f of x is exactly 0. So the equilibrium points are, and this function has and the roots of the nonlinear function f. So x goes to this equilibrium as time tends to infinity. Here's an example. Let's see. equation. It has two states x1 and x2. So the first function is we have to talk about the stability of the system. So you can observe that we are not given what v of x should be. And mentioned in one of the previous questions. And one of the obvious choice for the Lagrange function is this norm of square. So for our case, it is just x1 squared plus x2 squared. Okay, so if this is the case, that the first two conditions are met, of course. And since this is a nice polynomial function, we have also has continuous partial derivatives. And now we need to compute what v dot of x is. This is going to be, so you can see that v is a function of x1 and x2, and x1 and x2 are functions of the time t. So now we just have to apply the chain rule. First one is del v by del x1. Let's see the x1 by del t, dx and dt. Similarly, del v by del x2. Yes, so this is actually x1 dot and this is x2 dot, which you can substitute from the dynamics. So let's see. What is del v by del x1? It's simply 2x1. Substitute x1 dot. So see, we're going to get x1 cube minus x1 x2 square. Then this is going to be 2x2 times x2 dot minus x1 square x2 minus x2 cube. Yeah. Yes. Yes. Yeah. Exactly. Yeah. Yeah. So wait a minute. So just a second. One. No, so the non-linear system, which that will okay. So we have some perfectly stable in March. There's marginally stable. There's linear and because it's not linear and stable. Hmm. Okay. And I think for the purposes of this course, you can always assume a simple positive function like this one. I would suggest that you start with this one, and if you get stability in the answer, you should select that answer. Because if they have not supplied or they have not given a Lagrange function, then it's always assumed that you choose the simplest one. If they wanted you to check the stability with respect to some Lagrange function, they will give you that. You should like, if that's also a section of the system, I guess, so you can use the sections for the substitute. Yes. So And let's see. Okay, so we can simplify those sides. X1 square plus X2 square also. So this is always going to be positive. So this is always less than 0. This means that the equation or distributions is asymptotically stable. Conversion to check. This has this. I wrote this. So in of asymptotic stability in the last, we have that we have V dot as negative definite, and in addition, this scalar function goes to infinity as the norm of this range goes to infinity. So you can easily see that here also Vx, which is sorry, this is negative. Sorry, Vx is that the norm x squared. And you can see that as norm x goes to infinity, Vx also goes to infinity. So in addition to this, this is also asymptotically stable in the Lash. Just look at this condition once. Asymptotically stable, or if it's asymptotically stable, and asymptotically stable in the Lash as well. So we go on to the direct method for linear systems. Yeah. Okay. So here another example. Now we have a linear system. So x1 dot equals x2 and x2 dot equals minus x1 minus x2. So what's the matrix? 1 0 minus 1 and minus 1. So it's a linear system. The obvious choice for Vx is x1 squared plus x2 squared. Okay. So now we determine stability. The next step is to compute v dot of x. This is simply 2x1 x1 dot plus 2x2 becomes 1 plus 2x2. And we just need to substitute the dynamics there. So is this function v dot of x negative definite, or that's what it should be 0 0 0 1. Now you can also check that this has to be negative semi-definite, because in addition to 0 0, and for this v dot f is obviously 0, but for this choice, so the content which is the non-equilibrium condition, non-equilibrium point, v dot of x is still 0. So v dot f is negative semi-definite. really hard. So to determine stability, what we require is beta should be strictly less than zero. As you were pointing out, maybe we can use some other Lagrange function. So there is one other choice, which is again x1 squared plus x squared. Let's see. Half. So now you can check. So I'm going to write this down. V dot x, you can see del v by del x1, x1 dot plus del v by del x2, x2 dot exactly x1 exactly negative definite. And now you can comment on uh, the equilibrium being asymptotically stable. So this implies that the equilibrium stress of Lagrange function, and also Vx, which was this one, goes to infinity as norm x goes to infinity. So norm x here is x1 square, x2 square. This implies that the equilibrium is also asymptotically stable in the large. So for linear systems, we have a condition on the matrix P and also the matrix Q, which can determine the stability of the equilibrium point. So this is direct method of Feynman. So we're talking about asymptotically large wave condition. So if we can find so there is this Q, which is symmetric, possible definite, such that V transpose P plus P equals minus Q. Choose a matrix Q. So given a matrix Q, there exists P positive definite such that this holds. Okay. To check stability by this condition, we need Q to be symmetric and positive definite. So one of the obvious choice always will take the identity matrix. For a 3 by 3 system, this will be identity matrix of size 3. So let's see. There is a linear system which has been given. This. No. You can take something else, maybe some multiple of the identity matrix or some positive definite and symmetric matrix 3. You don't want to Yeah, as long as it's symmetric and positive definitely. That's the only condition. Yes. Yes. Yes, exactly. Yeah, because then this equation would change. When the right hand side of the equation would change, so the elements of the P matrix would also change. Because it's an if and only condition. So that gives you a, I'm sorry, can you repeat it? Okay, no, I mean, it's like we choose a matrix Q, for example, identity or something. And if this equation can be solved by a positive definite and symmetric P, then the system is stable. A different Q. Yeah. Yeah. Okay. Okay. Yeah. Then P would be a different matrix, but it has to be symmetric and positive definite. Since it's a linear system. Yeah. Yeah. Yes. Yes. That is one. I will. This kind of question is similar to the one in which you were talking about that Lyapunov function also does not need to be unique. Right? There could be this x1 plus x1 squared plus x2 squared, and there could also be something like this. So the function b here, or similarly, the choice of q here is not unique. As long as they satisfy positive definiteness and this symmetric condition, it's fine. This, for example, one of the matrices that we have. Again, the q that I'm choosing is the identity one. You are free to choose any other matrix you want. So let's see. He has to be symmetric. So these are going to be equal. And now we just have to substitute the matrices A and Q in this equation. So let's do that quickly. All right, now we have to create all the four elements of the matrices. So the first one is, wait, let me check. This is correct. So minus 2, P1 to equals minus 1. This is one of the equations. Let's repeat it. Okay. When we have P12 from here, so P11 minus P22 equals 0.5. Yes. P11 minus P12 minus 1. We have twice of this equals minus 1. So P12 is P2B minus half. So we have P2 as 1. And from the situation, data P1 is 1.5 plus P2 plus 1.5. So the matrix that we get is 1.5 comma. Okay, this is positive definitely. And it's also symmetric. So we have that. The point is that given a Q matrix, we find P which is positive definite and symmetric. If we started with some different choice, for example, some Q prime, then if P is positive definite and symmetric, then the system would be stable. The property of this linear system would not change. That is because we started with some different Q, we would get a different P, and that would also be positive definite and also symmetric. Okay. Now let's see the question. Okay. So now the variable is y, so y1, y2. So that is -1, -2, 1, and -4, -1. Then just for simplicity, choose this as identity matrix and find the solution for this. I'm going to write down the P matrix already. You can cross check later. So minus 23 over 60 minus 7 over 60. Now we can check that 4 is symmetric and it's a positive definite. So we have asymptotic stability in the latch. We have one more question, but it's a maybe. Okay, so again, we have a linear system, but it's not a homogeneous one. So let's see. Second order system, x1 dot x2 dot, this is minus x1 minus 2 x2 plus 2. Then what? x1 minus 4 x2 minus 1. So if you see in the lecture notes, the system that we're considering for direct method of Lyapunov is x dot equals a of x. But if you observe here that we have some constants here and we want to transform this system into a homogeneous system. So what we can do is a change of variables and maybe defining new states. So let's see. Combination of x1 and h2 such that we have y dot equals a of 1. Then we can apply the direct method of Lyapunov to the system. Okay. Diagram which is just some transmission of x1, and y2 is just some transmission of x2. Right. So now we have to complete what y1 dot and y2 dot are. This is simply the y1 and y2 now. So this is going to be plus a minus b/2 plus bb plus 4. Sorry, plus 2. Then we have some squares. Then we write down what y2 dot comes out to be. So y2 dot is x2 dot, which is nothing but x1 minus 4x2 minus 1. And this becomes, so we have to substitute this in terms of y1 and y2. This is y1 minus 3 minus 4 times. We get y1 minus 4/2 minus 8 plus 4b minus 1. There are some extra terms in the differential equations of y1 and y2. And to get the homogeneous form in terms of the variable y or the states y, there are two conditions, right? So one of them is a plus 2b plus 2 should be 0, minus a plus 4b minus 1 should be 0. So you can compute what a and b should be. From this, you can compute what y1 and y2 are going to be. So this is the change of variables or the change of states that we wish to have, so that we have the system now y dot equals a of x. Okay, so what is the matrix A here now? The A that we got is from here, it is minus 1 minus 2, 1 minus 4. Okay, so we have a homogeneous system, we have the matrix A. Now we are going to use the direct method of diagonal comment on the stability, asymptotic stability. So transpose B plus BA equals minus Q. Here, as before, we are considering with the identity. And now by substitution of this P, and comment on the stability of the system. Okay. So this stability is only valid, or asymptotic stability is only valid. You get some values of A and B by satisfying these two equations. Okay. So another question that we have is this. So for example, we have a linear system. We have a third order system. First order differential equations. We have x2 minus x2 plus x3 and then minus 4x. Now the question is, we find J that the system. So let's see. X dot is asymptotically stable. So there is one more data that we have. We have been given the Lyapunov function to determine stability. So this method is not the direct method of diagonal. So we have this VFX, which is something we understand. X1 squared is 2k x1 x2 plus 20 x2 squared is 2x3 plus x3 squared. So this is given. And we have to determine stability. So this will be easy. Just check if, well, before this, just check if this is positive definite. Just check if it's 0 at 0. Only it's 0 at, sorry, 4. So x1 can be 0. X2 has to be 0 for the first. And x3 has to be again 0. Okay. So you can either check like this or you can form the P matrix X transpose Px and then comment on if it is positive definite or not. We symmetric and positive definite. So in this case, it's going to be a 3 by 3 matrix. Check this by Sylvester by taking the principal minors and checking their signs. Okay. So Vx is positive definite. We comment on stability. Now we need to compute V dot of x. This is very straightforward. This is 10 3x1 dot. So now we have changed plus 2x2 dot. X1 dot h2 dot and c dot. You can substitute those here and then find v dot of x. So write down the expression that we get. You can check this after this session. This is minus 40 minus 2k x2 square. This table is going to be a condition on k such that p is positive definite. And we will also get a condition from k here such that v dot x is negative. Negative semi-definite. Okay. K should be less than 20 and should be greater than 0. So if I've taken control systems course before, this was also like the case in which you have to form the route table and there is a constant in the characteristic equation which you need to determine so that there are no sign changes in the first column so that the system is stable. So here what we are doing instead is considering the lab on a function and then determining the value of k. Greater than 0, that is it. K should be less than 20. Yeah. Also get this equation on this from maybe that P should be positive definite. You'll get something on K. Alright. So if you have any doubts regarding this week's assignment, you can ask me now. Yeah. Okay, I think I've done. Okay, so not sure. Try to do this on MATLAB. I mean, get the root of this fourth order equation. Mm. Okay, but this is a transfer function, right? You already know how to compute the poles of the transfer function. Which actually, yes, but you already know how if you have a characteristic, I mean, if you have the characteristic polynomial of the transfer function or the denominator, you know how to complete the poles without actually solving this equation, right? I think I did this today. That if there's a large third order system and you don't wish to compute the eigenvalues, and if you have the transfer function, or is the route table, I guess. I mean, that could be one of the ways. Yeah, right. In. So this was the equation, third order polynomial. So instead of finding out the roots, what I am doing is now targets check. So you just form this table and determine the sign changes here. Have you done this before? Yeah, right. I mean, you already have a transformation. Wait, this route of it still depend on pole zero. So, wait. Hmm. Uh, I guess from the route suggest that you can just check if it is either stable or not stable, right? I don't think the question asks for asymptotic stability at all. It says determine the stability of the given system. So, it's, okay, so it's a linear system. I think it's just talking about bounded input, bounded output. Out of its criteria, it would be marginally stable if the roots are on the imaginary axis. And if there is even one sign change, then it would be that the root is on the right hand side, then it would be unstable. Because one thing that you can check is this fourth order polynomial. Does it have roots at -4 or -5? Did you check that? Mm. Did you have doubt in any other question? Or is that it? 10 is you can choose norm as well. That is well. So maybe let me just check question number 5 if router is criteria is applicable or not. I should on the announcements portal. Is that all right? And then there is a discussion forum, I guess, somewhere. Yeah. Okay, so this is all right. Just one second. So maybe I'll just open a new discussion and then uh, maybe there is that question of it. Tell you about what question 5 should be, okay? Thanks. So let's wait for today. Thank you.